Hello dear students. Our lesson for today is all about minerals. In this lesson, you should be able to make a plan that the community may use to conserve and protect its resources for future generations, and identify common rock-forming minerals using their physical and chemical properties.
Mineral is a naturally occurring, not man-made or machine-generated, inorganic, not a byproduct of living things, solid with an orderly crystalline structure and a definite chemical composition. Minerals are the basic building blocks of rocks. Minerals make up the rocks beneath your feet, the soil that supports plants, and the deep rock of Earth's mantle. Any thorough study of Earth must include an understanding of minerals. But it is not sufficient to study minerals isolated from the rest of the planet. Rather, we can learn more by observing the ways that minerals interact with other Earth systems. Before we continue, let's answer some questions. Firstly, do you consider water a mineral?
If you answered no, you're right. Because water is not solid and crystalline. Let's try another question.
How about snowflake, or tube ice? Are these minerals?
Well, tube ice is not a mineral, because it is not naturally occurring. But a snowflake possesses all the properties under the definition of a mineral. If you guessed all the answers correctly, great job. But if you didn't, worry not, because as we go through our lesson, you will learn everything about minerals and be able to identify if something is a mineral.
Minerals are not always hard to find. Actually, we are using these products made from minerals daily. Graphite is the mineral used in wooden pencil. Halite is the mineral found in salt. Your cell phone is made up of different minerals, like gold and silver. The cars that we drive, the roads that we travel, the building that we live in, are some examples of products derived from minerals. There are 5 characteristics of minerals that we can use to identify them. First, naturally occurring, or a product of Earth's natural processes. Second, inorganic, or it must be product of Earth's physical processes. Third, homogeneous solid, minerals should have definite volume and rigid shape. Fourth, definite chemical composition, it must be represented by a chemical formula. And fifth, orderly crystalline structure, the atoms of minerals are arranged in an orderly and repeating pattern. There are several different mineral properties which must be identified and defined. First, we have luster. It is the quality and intensity of reflected light exhibited by the mineral. It can be metallic, generally opaque, and exhibit a resplendent shine similar to a polished metal. Or non-metallic, vitreous, glassy, adamantine, brilliant, diamond-like, resinous, silky, pearly, dull, earthy, greasy, among others. Next, hardness. It is a measure of the resistance of a mineral, not specifically surface to abrasion. Hardness scale is designed by German geologist mineralogist Friedrich Mohs in 1812. The Mohs scale of hardness measures the scratch resistance of various minerals from a scale of 1 to 10, based on the ability of a harder material mineral to scratch a softer one. The Mohs scale of hardness measures the scratch resistance of various minerals from a scale of 1 to 10, based on the ability of a harder material mineral to scratch a softer one. However, there are pros and cons to using the Mohs scale. Pros are, the test is easy. The test can be done anywhere, anytime, as long as there is sufficient light to see scratches. The test is convenient for field geologists with scratch kits who want to make a rough identification of minerals outside the lab. While the cons are, the scale is qualitative, not quantitative. The test cannot be used to accurately test the hardness of industrial materials. You can see on the picture on the right that the Mohs hardness scale is organized from the softest to the hardest. For the softest one, we have talc, followed by gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, and the hardest is diamond. The third property of minerals is its crystalline habit. The external shape of a crystal or groups of crystals is displayed or observed as these crystals grow in open spaces. The form reflects the supposedly internal structure of atoms and ions of the crystal mineral. It is the natural shape of the mineral before the development of any cleavage or fracture. Examples include prismatic, tabular, bladed, platy, reniform, and equant. A mineral that do not have a crystal structure is described as amorphous. Next we have color. A lot of minerals can exhibit same or similar colors. Individual minerals can also display a variety of colors resulting from impurities and also from some geologic processes like weathering. Examples of coloring: quartz can be pink, which is called rose quartz, amethyst is purple, citrine is orange, and colorless quartz. Next, streak. Streak is the mineral's color in powdered form. It is inherent in almost every mineral and is a more diagnostic property compared to color. Note that the color of a mineral can be different from its streak. Examples of streak: pyrite exhibits gold color but has a black or dark gray streak. The crystal's form also defines the relative growth of the crystal in 3 dimensions, which include the crystal's length, width and height. Next, cleavage. Cleavage is the property of some minerals to break along specific planes of weakness to form smooth, flat surfaces. Planes exist because the bonding of atoms making up the mineral happens to be weak in those areas. When minerals break evenly in more than one direction, cleavage is described by the number of cleavage directions, the angle at which they meet, and the quality of cleavage. Cleavage is different from habit; the two are distinct, unrelated properties. Although both are dictated by crystal structure, crystal habit forms as the mineral is growing, relying on how the individual atoms in the crystal come together. Cleavage, meanwhile, is the weak plane that developed after the crystal is formed. Next, specific gravity. It is the ratio of the density of the mineral and the density of water. This parameter indicates how many times more the mineral weighs compared to an equal amount of water, whose specific gravity is 1. For example, a bucket of silver, with specific gravity 10, would weigh 10 times more than a bucket of water. Next, diaphaneity, or the amount of transparency. It is the ability to allow light to pass through it. This is affected by chemical makeup of the mineral sample. As you can see on the picture, the crystal is able to pass light. Other properties of minerals include the following. Tenacity describes the mineral's reaction to stress. Brittleness, a mineral turns into powder. Malleability, a mineral can be flattened by pounding with a hammer. Ductility, a mineral can be stretched into wire. Flexible but inelastic, minerals are bent but they remain in the new position. Flexible and elastic, minerals are bent, and they bring back to their original position. Sectility is the ability of a mineral to be cut into thin pieces with a knife.
Minerals, like many other things, can also be categorized. The most stable and least ambiguous basis for classification of minerals is based on their chemical compositions. We have the native elements: gold, bismuth, and diamond; silicates, quartz, olivine, and talc; oxides, hematite, magnetite, and chromite; sulfates, gypsum, barite, and anhydrite; sulfides, pyrite, galena, and bornite; carbonates, calcite, dolomite, and malachite; lastly, halides, chlorine, fluorine, and halite. The elements listed below comprise almost 99% of the minerals making up the Earth's crust. Namely, oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, and all the other elements.
Silicates are minerals containing the 2 most abundant elements in the Earth's crust, namely, silicon and oxygen. When linked together, these 2 elements form the silicon-oxygen tetrahedron, the fundamental building block of silicate minerals. Over 90% of rock-forming minerals belong to this group. Oxides are minerals composed of oxygen anion O2 combined with 1 or more metal ions. Sulfates are minerals containing sulfur and oxygen in the form of the SO4 anion. Sulfides are minerals containing sulfur and a metal. Some sulfides are sources of economically important metals such as copper, lead, and zinc. Carbonates, minerals containing the carbonate anion combined with other elements. Native elements are minerals that form as individual elements. We have metals and intermetals, minerals with high thermal and electrical conductivity, typically with metallic luster, low hardness. Semi-metals, minerals that are more fragile than metals and have lower conductivity. And non-metals, non-conductive, sulfur, diamond. Halides are minerals containing halogen elements combined with 1 or more metals. For the evaluation, let us answer the following. Summarize the different characteristics that define a mineral. Answer: inorganic, naturally occurring, crystalline, solid and must have a consistent chemical composition. Which among the following mineral groups, if any, contain silicon, halides, carbonates or sulfides? Explain. Answer: none. The identified mineral groups are non-silicates. Which is more abundant in the Earth's crust, silicates or all the other mineral groups combined? Explain. Answer: silicates. Silicon and oxygen are the main components of silicates, and these are the two most abundant elements in the Earth's crust. Fourth, an unknown opaque mineral has a black streak and has a density of 18 grams per cc. Is the mineral metallic or non-metallic? Answer: the mineral is more likely to be metallic because it is opaque, and metallic minerals are usually heavy and with dark streaks. How does streak differ from color, and why is it more reliable for rock identification? Answer: streak is the color of a mineral in powdered form. It is more reliable because it is inherent to most minerals. Color is not reliable because a mineral can be formed with varieties of color, an effect of impurities and weathering. Differentiate between habit and a cleavage plane. Answer: habit is the external shape of a crystal that is developed during the formation of the mineral. A cleavage plane is a plane of weakness that may develop after the crystal formation. Seventh, is it possible for a mineral to have a prismatic habit without having any cleavage? Why or why not? If yes, give an example. Answer: yes, the prismatic habit is simultaneously developed while the mineral is growing. During the process, there is no repetitive plane of weakness being created, which makes the mineral break only by fracturing. An example of this scenario is quartz. Define rock-forming mineral, and give 3 examples. Answer: a rock-forming mineral is a mineral that is common and abundant in the Earth's crust, one making up large masses of rock.
That's all for today. I hope that you learned all about minerals. For your activity, answer the following on your notes. Learning Task 5, page 16. Learning Task 6, page 17 to 19. Learning Task 7, page 24 to 25 and page 27. Have a nice day.